Good day all. Today we are looking at the types of logic gates. We will be talking about the 7 types of logic gates with 3 inputs, their symbols, and their behavior through the help of a truth table. Let's begin. First, we'll be looking at OR gates 3 inputs. Our symbol of OR gate is denoted as your input, then a curve and another curve, then your output. So it is important that you note that it's a curve and a curve. Then you have your A, B, and C representing your 3 inputs, and your Z, which is the output and is the summation of the 3 inputs. Now let's draw our truth table. Now there is a way to know whether a way to know the number of ways our input can vary. Now, how we get this is using this formula 2 raised to power n. N is the number of inputs, where n is the number of inputs. So in this case, our n is 3. So we're going to be having 2 raised to power 3, which is going to be giving us 8. So we are going to be having 8 ways our input can vary. Now, I also like to say that we don't start from 1 to count, but from 0. Now you have your 0, and because of that, we won't be having 8 at this region, but 7, due to the fact that we're starting from 0 to count. So your 0, 1, 2, 3, 4, 5, 6, and 7. Now, for your distance, for your OR gates, I'm trying to represent the whole of this into its binary form. Now, for your 0, in its binary form, you have 0, 0, and 0. That's for your input. For 1, you have 0, 0, 1. For 2, you have 0, 1, 0. For 3, you have 0, 1, 1. 4, 1, 0, 0. 5, 1, 0, 1. 6, 1, 1, 0. And our final boss, 1, 1, 1. Now, this is the way our input is. This is the way we arrange our inputs. Now, for us to find our outputs, we'll simply add the inputs together. So for this, 0 plus 0 plus 0 is 0. 0 plus 0 plus 1, 1. 0, 1, 0, 1. 0, 1, 1. Now that's is meant to be 2. But since we're dealing with binary and not binary, that of logic gate, we're only dealing with we're meant to be having one output here. So long there is a 1 here, we'll just say 1. 1, 0, 0, 1. 1, 0, 1. So long as there's a 1 there, 1. 1, 1, 1. 1, 1, 1. 1. So you can then say for your OR gates, your truths for your OR gates, your your output is high when as long as one of your inputs is high, and low when all of your inputs is low. I will say that again. For your OR gates, your output is 1 so long that at least one of your inputs is what? 1 or high, and low or 0 when all your inputs are low or zero. So that is for your OR gates. Now moving over to your AND gates. Okay, that will be necessary. That will be necessary. I will just clean some parameters since we're only interested in the attributes, because that's only what varies and not the inputs. Where our truth table will change is when we are dealing with not. That is when we just need only 2. But for now, there was no need for us cleaning the input since it remains the same. And in case if you are confused on how we got our values, I will make a quick explanation on that. So let's say we want to find 4. Now converting 4 into binary, you simply do your 2, find something more like an LCM, but divide 2 by 2 only. So your 2, 4. This is your 4. We're trying to find its binary form. So we'll be dividing by the unit of binary, which is 2. So 2 into this, you have 2 remainder 0. 2 into 2, 2 into 2, you have 1 remainder 0. 2 into 1, you have 0 remainder 1. So, and we take from down to up, giving you your 0. So that's how we got all this value. You can try it for all for the rest from 0 to, of course 0 will give you this. You can try for the rest 1, but if you try for 1, you will just end up having just 1. But you will put it, I will start from the extreme side and coming towards the left hand side, and from the way we count. So this is the value for our 1 in binary, and for others you can try them using this pattern. You will still get this step in case if you're wondering how we came about the value. Another way you can also get the value or maybe have it off heart is by counting like this: 0 1 0 1 0 1 0 1. Then the next one you start in twos. The first one you count single. Then the next one you count 2 of this one, 2 of this one, 2 of this one, 2 of this one. So 2 0 2 1 2 0 2 1. Then the next one 4 0 0 0 0 1 1 1 1. If there's to be another one, another input, let's say we are dealing with 4 inputs.
That one will then be 8 zeros and 8 1.
So it follows that order. So in case if you don't have time to start deriving all this, or you don't have this off heart, you can just follow that procedure and you still get this table. So it's not something you memorize. It's quite easy. Now for us to get our output for AND, our diagram here will change. Only what we change is just the curve in the front. There is, in our AND, the difference from that and OR is that there is no curve but a straight line, then your curve. So this is how your AND is represented as a straight line with the curve, while OR is a curve and a curve. So for AND, this won't be addition anymore. This time around we are dealing with multiplication. Of course, in our multiplication table, we know that 0 multiplied by anything is 0. So knowing that, we have this to be 0. 0 times 0 times 1, 0. 0 times 1 times 0, 0. 0 times 1 times 1, 0. 0 times 0 times 1, 0. 1 times 0 is 0. 0 times 1 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 times 1 times 1 is 1. So this is for your AND gates. Your AND gate with 3 inputs. This is how your table looks like. Now, here we can see that so long one of our inputs is low, our output will definitely be what? Low. So long one of our inputs is 0, one of our outputs will be 0. But so long but when all the inputs is high, our output is high. When all the inputs are 1, our output is 1. So that's for your AND gates. Now we'll be moving over to that of NOT gate. I won't clean the table. Instead, I will be drawing at this part of the board, because we need this table for the rest. Let us not use because of NOT and clean this table. So this remains for our 3 input. But since we're not dealing with NOT, which is the bus of its own, that only demands 1 input, 1 output, and our diagram also changes. We are another name for your NOT gate is inverter. This is how our diagram looks like. 1 input, 1 output, and the major thing that you shouldn't miss is a 0. There's a kind of a 0 or a circle at the mouth of the symbol. That is even more important than the triangle itself. So it's either this circle is at the front or at the back. So in case if you're having an input A, your output will be Z, which is simply just the complement of A. What A and what A is not, the opposite of A. That is what your Z is. That's the meaning of that line on top of your A. So for each truth table, remember we're not making use of this because we only have 1 input, 1 output, and we can only have, and using that our formula, which is 2 raised to power n. Now our n here is 1 because our number of input is 1. Now putting this here, we know that our answer is what, 2. So we can only have 2 ways that the answer can vary. 2 ways that the answer can vary. Now knowing this, our table will look like this: your A and your Z. One, no, 0, 0, 0. No, no need for writing. This will confuse us. 0, 1, and 1, 0. Since our input is low here, our output is high. Since our output is high here, our input will be low. So that's just what NOT is about, just the negation. What the input is not, that's what you see at the output. So we are done with the special man. Now let's return back to our three input system. Our 3 input system. Please note that NOT is not 3 input but 1 input. It doesn't accept more than 1 input. So the next one we'll be dealing with is our NOR, which is not OR gates. The kind of combination of the NOTs, which is the negation of the actual value, and the OR gates. So when you do, the idea here is when you do your addition with your OR gates and you get your answer, you still find you find the opposite of that answer. So for clarity's sake, let us make a room for OR. Our symbol, the symbol for NOR, is your OR. Now with the circle in front. These are your inputs: A, B, and C. And this is Z, which is your A plus B plus C complements. What the addition of all this is not. So let us go. 0 plus 0 plus 0 gives us 0. What is 0 not? 1. 0 plus 0 plus 1 is 1. What is 1 not? 0. For this, we have 1. Let us just fill in our all values. We have 1. We have 1, 1, 1, 1. Remember, so long there is one high value, there must be a one high input, there must be a high output. Now, knowing this, we can now get our OR, which is just the negation of whatever is here. So we have gotten the first one, 1 and 0. The next one follows 0, 0, 0, 0, 0. Now this is the table for our NOR. Now we don't need this. This was only here for clarity sake. This is the actual value of our NOR. Now we can now see that as long as one of our inputs is high, the output will be what? Low. But so long all the inputs are low, our output will be high. That is what our NOR does. And I'd like to say something because when I was going through this, I almost got confused. I was thinking that your NOR and your AND are kind of saying the same thing. They are not. If this was to be for your AND, if this was to be for your AND, here we have 0, 0, 0, 0, 0, 0, 0, 1. So they're not the same thing. Why this is telling us that so long there is one low input, the output will be low. As long there is one so long the inputs, the three of them are high, your output will be high. This on the other hand is telling us that so long there is a high input, your output will be low, and so long there is no high input, your output will be high. So they're not the same. I'd like to clarify that. Now, instead of us cleaning this of our AND, we can now move over to the next gate in line, which is your NAND. Your NAND is just the opposite of your AND. It is the complete opposite of your AND. Now our symbol will also change. This won't be it is represented. Remember, our NAND normally has a dash, a straight line, and not a curve, and it is product and not addition. Okay, so whatever your product is not is what your output is meant to be. So we have already gotten what our AND is. Now for us to get our NAND, we simply just negate what the AND is. So the AND here is 0. So here will be 1 for this, 1, 1, 1, 1, 1, 1, and for this 0. So this is what our NAND gates is. This is the outcome of our NAND gates. So what it tells us is that so long one of the inputs is low, so long one of the inputs is low, the output will be what? High. So long one of the inputs is low, the output will be what? High. But when all the inputs are high, our output will be low. Our output will be low. So we are done with the universal gates. Now let's move over to that of the XOR and XAND. Starting with the XOR first. Let's clean this. Okay. So starting with the XOR and XNAND. No, not NAND. XNOR and not NAND. You don't have XNAND. We don't have X and X NAND. These are wrong. So bear that in mind. No such thing exists. We don't have this. Now, for your XOR, our symbol, since we're dealing with OR, that means we're going to be having a curve. This is exclusive OR gates. That's what the X stands for, exclusive. So we are having 3 inputs and your OR, no, and your exclusive sign first. Then your OR, then your OR gates. Okay, we're not dealing with NOR yet, and then this. Now these are your inputs A, B, and C. These inputs, and your output, which is Z. Our output Z is our XOR. We represent it with a plus in a circle. Let me write this in a bigger way because it won't enter there. So our output Z is A, C. So this is how we represent our exclusive. This is how we represent our exclusive. For our output, the idea here is to look at your input. If there are odd numbers or odd value of high inputs. When I say odd value, for instance, how many high inputs is there? We have one. How many high inputs is there? We have one. But how many is there? We have two. So this is for your even. 2 is an even number. 3 is an odd number. 2 is an even number. 1 is an odd number. So now since we know our the ones that are odd and the ones that are even, here there is no high inputs here at all. So the idea here is to look at the our inputs. If we have an odd number of high inputs, then our output will be high. But if we have an even number of high inputs, then our output will be low. And if we have no high inputs, our output will be also low. The reason I'm saying this is because of this first one. So for this one, we will have that our input is what? 0. For this odd number, only one high input. This is an odd number of inputs. So we are having what? 1. The same thing goes for this one. 1. But for this, we are having two high inputs. So our output will be what? 0. This we are having one high input. So our output will be 1. Over here it will be 0 because we have even 1 and 1, which is 2 high inputs. So our output will be 0. Even number of inputs. So our output will be what? 0. Then this odd number of what? Odd number of inputs. Then our output will be what? High. Odd number of high inputs. So our output will be what? High. So this is for the OR. You can take a look at it. I will recap once more. The idea here is to look at our high our inputs, especially at the high inputs. How many are they? Are they even in number? Are they even in number? If they are even or if they are odd, that's what determines what our output will be. So looking at each of these inputs, for the first one, we have no high inputs there. So we take this to be 0. I don't know if 0 can serve as an even number, but 0 mathematically may not classify to that. So we're taking it to be so now. So since there is no high input here, we say this is 0. Over here, since we are having only one, which is an odd number, only one high input, we will have that our output will be what? High. Only one high input, our output will be what? High. 2 high inputs, our output will be what? Low. One high input, our output will be what? 1. 2 high inputs, our output will be what? 0. 2 high input, our output will be what? 0. And 3 high input, our input will be what? 1, because 3 is an what? Odd number. So that is for your XOR. Now for us to get our XNOR. Okay, sorry. Let's clean this. Now for our XNOR, the diagram remains the same, only just that at the tip of your OR. Okay, let's start with the name. XNOR. So like our normal NOR, that's having a 0 in front of it, we added this to this. So the line in front is for your exclusive symbol. So that's what it denotes. So this is the symbol for your XNOR. This is the symbol. So it is what the XOR is not. So for us to know what the XNOR is for us to know what the XNOR is, we have to first of all know what the XOR is. The XOR, we need to know what that is. So let me also make an extra table for our XOR in order not to get us confused. So this is for our XOR, and the next, this is for our XNOR. Okay, so for our XOR, like we said earlier, we're looking at the values if they are odd or even. So if they are odd, it is if they are odd number of high inputs, the output will be high. But if there is even number of high inputs, our output will be low. This is the opposite, meaning that if there is even number of, okay, let's also derive it, then we'll say that. So for our XOR, we know this is 0, 1, 1, 0, 0. No, sorry, this is an odd number. 0, 0, and 1. So this is what this one is not. That's the opposite. And we're having 1, 0, 0, 1, 0, 1, 1, 0. So moving this tells us that if we have an even number of high inputs, our output will be what? High. But if we have an odd number of high inputs, our output will be low. Our output will be low. So over here we are having an even number of high inputs. We have no high input actually here, so our output will be what? High. Here we have an odd number of high inputs, our output will be low. Here we have a odd number of high inputs, our output here will be what? Low. Even number of high inputs, our input here will be what? High. And even number of high inputs, our output will be what? High. Even number of high input, our input will be high. Odd number of high input, our input will be low. So this is all we need to know about the types of logic gates. Please don't forget to subscribe. Thank you and God bless you.